Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistor, a physics perspective. This is lecture number 48 and we will be looking at negative capacitance and improved threshold swing of the device. Now let me, we have already seen in our previous lecture what do you mean by negative capacitance FET. Now we have also seen to quantify the value of S, and if you look at the quantification of value of S, what comes out is on the left hand side, if you see, it is 1 minus C division upon 1 by C NC minus 1 by C ox, and that is what you get out of it. Negative sign is coming because of the fact that your NC is actually having a negative capacitance, and that is the reason you see a negative value coming into picture here. So the left hand side gives you a negative cap and the right hand side gives you the traditional non-negative capacitance devices which is available to us, right. Now the left hand side is again in electrostatic, and on the right hand side we are actually looking into the transport limited, means are you applying a drift diffusion model for all your practical purposes, and you get something like this here. And as you can see, when EC equals to EF in the first part, then e to the power 0 becomes equals to 1, and you get 120 here multiplied by ln of 1 plus n, that comes out to be 120 multiplied by ln of 2 multiplied by that will give you the effective value of the subthreshold slope on the right hand side blue part, right. And these are the various contributions from electrostatic and transport phenomena. So if you look at overall MOS capacitors because of this thing, we will write it down as C div dot. So it's basically sort of parallel in capacitance, a series combination of C div and C ox, right. And you will get C div dot C ox upon C div. C div we have already defined in our previous lecture. It consists of quantum capacitance, it consists of traps, it consists of source drain infringing field capacitance, and so on and so forth. And that is what you get for NC layer as well. Now if you look at the subthreshold slope swings SS, and as I told you that if M is greater than 1, AV is basically my internal voltage gain, right. AV is voltage gain, and we define that to be as, so if you look carefully here, if you look at this particular point, then this whole idea here is 1 minus CMOS by CNC less than VTH. When you are in the subthreshold region of operation, and if you divide by CNC, you will get this to be, so we will get 1 by AV to be less than 1, which means that AV will be greater than 1 in that sense, right. This tells me that CNC also has a capacity to do an internal voltage amplification, right, and will achieve to you a better one. And therefore, and two things therefore come into issue. One is a body factor of greater than 1, right, and a voltage gain greater than 1. They will compete with each other in determining the subthreshold slope. Higher the value of M, higher will be the value of SS, but higher will be the value of AV, lower will be the value of SS. So they will fight with each other, and finally a fixed value will be concentrated in this particular case. Now let us look at visualizing the subthreshold formula and its physics. Now if I plot 1 by C NC on the right hand side on the x axis, right, 1 by C versus SS, and SS you normalize with respect to 60 millivolts per decade. So what you get is that this 1 basically is the limit, Boltzmann-Tirani limit, and anything beyond this is not a good idea, right, because M is going on increasing beyond 1, right. Anything at this particular point where M is below SS by subthreshold slope is below 1 modified value is a good idea in terms of having a much better design. Now in the shaded region on this side, we will see that this and this shaded region actually, if you look very carefully, M dominates, and therefore subthreshold slope is always greater than 60 millivolts. This on the left shaded region, SS is always greater than 60 millivolts per decade. Why? Because here the body factor dominates. On the right hand side, the subthreshold slope is actually negative in a sense, less than 0. This is the appearance of hysteresis or negative capacitance, and the design space between negative value and a positive value of M is where your AV or the voltage gain dominates, and your SS is between 0 and 60 at this particular plates, and this is where your internal voltage gain dominates, right. and that is the place where you want to work ideally in case of devices with higher slopes. Now let's take that graph and apply it to a quasi-static device physics of NC-FET. Now on the left hand side, if you plot log ID versus Vg, so as the Vg increases, you see the brown curve, it goes on increasing. But because of negative capacitance, you suddenly see the current is actually increasing with reduction in the value of Vg. And this happens because of, with a decrease in the value of Vg, you still see a large value of change in the charge, and that is the reason the current increases. But then this won't be visible to you in the standard oscilloscopes or anywhere else, right? So you won't see this part, but after that you see a flat region which you see here. And we are assuming that my CMOS in post threshold is much larger as compared to your CNC, which is the negative capacitance FETs available here. However, there is a problem here. The problem is that the value of your CQ, right, that narrows the NC design space. The CQ which is there, it does not allow you to go. So you see this white region, small white region which you see. If you look at this blue curve here, this is the value of S by TP. If you see, then at it, if I want to work between m equals to 0, normalized value of m between 0 and 1, then my design space is only restricted to this small white region. And that is the problem, that you cannot let the capacitance of the device move to a large value, so that you won't get an internal voltage amplification in this case, right. The voltage gain AV is given by dVMOS by dVg, and it is given by CNC upon CNC minus CMOS. Now if you divide by CNC in the numerator and denominator, I get 1 over 1 minus CMOS divided by CNC. With the negative sign you will get. I will obviously use the MOS mod value here. This is where an interesting thing comes into picture. See, when your CNC mod value becomes of the order or at least equal to CMOS, this quantity reaches to a 1 value, right, and therefore this quantity whole shoots up, the voltage gain becomes very large, almost infinity. And this is one of the design criteria which people follow for achieving a larger voltage gain, that if you are able to maintain CNC very close to CMOS, both together almost equal to each other, your voltage gain increase. Easier said than done, because designing it is a very difficult task in actual fabrication. Now this is a schematic of an NC layer integrated with gate oxide. We have already discussed this part, so I will quickly go through it. So I have this ferroelectric layer, I have the insulator layer, and I have this semiconductor, and followed by a metal at the top gate. So this is MFIS layer, metal, ferroelectric, insulator and semiconductor layer, right. So this is what you see here. Okay, there was a very interesting modeling done, and this is known as Landau modeling for the negative. So this is where we enter into the modeling part of it rather than the device physics behind it, but the modeling part. And the Landau expression is given by this quantity. It looks complicated, but where delta P is basically the change in the polarization, delta T is the time domain change, delta T, right, and gamma, beta, alpha, rho are all constants, sort of empirical constants, and these are coefficients or Landau coefficients available. The variation of the free energy versus polarization. So if you change the polarization, how does the free energy change? On the right hand side, if you look at polarization versus electric field, as I discussed with you earlier, this is the curve which you will actually get, right, experimental if you do a PE curve, but if you do a LKPE curve, we will get this part, and that is where the negative capacitance, this is also known as an S curve, where negative capacitance comes. Let us break it down. So alpha P is basically the linear term, where alpha is the temperature dependent coefficient, right. At QD temperature, where ferroelectric goes to dielectric and so on and so forth, there is a change in the reversal in sign of alpha x, and therefore there is a change in the spontaneous polarization. The second term, which is beta times P cube, is basically a cubic term which gives you the nonlinear behavior and allows you to have a multiple polarization states available, whereas the first one allows you to only have the single polarization state available. The fifth order term is what causes the stabilization of the system by ensuring that the energy does not diverge at very high values of P. So what will happen is the gamma x value will have a very low value. So even if your P increases drastically in the order of fifth order, this whole quantity will try to damp it down, right. Rho x is defined as the damping of the viscosity coefficient, and is basically time dependent gradient coefficient. So what we have learned, at least from this basic LK equation, is that there are alpha x, beta x and gamma x. They primarily control the shape of the graph. So which graph? This red colored graph which you see here. Change the value of alpha x, beta x and gamma x, and you will see a change in the values, numerical values of these graphs here. The value of rho x and gx, rho x is basically damping factor and gx is the gradient coefficient. Rho x will actually introduce to you the time dependency of the dynamic model, which means that if you apply a bias and the bias is, say, sinusoidal signal, how does the behavior takes place with respect to time will give you by rho x. Similarly, gx gives you the spatial variation. So the wonderful part of this equation is that both spatial as well as temporal variations are taken care of in these equations. Let me come to LK parameters for specific materials, and they are given on the left hand side. You can have a look at these material values of alpha x and beta x. These are experimentally determined values, and on the right hand side you will see the empirical relationships for alpha, beta and gx, right. And so people use large amount of dopants, for example lanthanum, they use strontium, yttrium, zetrium, they use all zirconium, all they use as a dopant species. Now these are the results taken from this paper, where if you look at S curve for various materials, so D1, D2, D3, D4 till D7 are various materials available. But all the materials which show negative capacitance will show an S curve, as you can see on the left hand side. This S curve is always available to all the materials in that sense. The S curve is always available. Now interestingly, if you look at the blue curve, which is D3 basically material, the S curve which you see is from this point to this point, right. You have a negative capacitance, whereas for the green one, which is D2, it is between this point and this point, which tells me that the electric field at which the negative capacitance starts to take place is much higher for the D2 material as compared to for the dark blue colored graph. Similarly, if you plot the IDVG for various materials, they are done for the FinFET, and that shows you the various values here. One thing which we found out when people did all these experimentation was that if you have a lower beta value, beta x value, then you have a higher I off. So if you want to reduce the value of your off current, it is always advisable to keep your beta value to a slightly higher value. Then you can have a lower I off available, right. And the on currents are strongly governed by the alpha value. Alpha is the coefficient which you see. So if you look at the first graph here on the left hand side, it plots subthreshold swing versus various materials, different materials doped by different materials, and you can see that in some so you see in most of the cases except BL and D3, you will see that your subthreshold slopes are lower than 60 millivolt per decade. Similarly, if you look at ion here, BL of course is a much lower ion, right, but D2 has got the highest ion among all of them material. Similarly, if you look at I off, D4 has got the minimum one BL. So if you look at the BL one, which is the benchmarked one, has got the worst characteristics, but it seems D2, D and D4 gives you the best characteristics in terms of output operation. Now let us look at the impact of temperature. That is a very important thing to look into, that as the temperature changes, so if you plot alpha x versus temperature, it starts to fall down as you go for higher and higher value temperature. Temperature goes on increasing, there is almost a linear fall in the value of alpha. So that gets reflected onto the PE curve of a negative capacitance device. And as you can see, as you go from 250 Kelvin to 350 Kelvin, the S curve becomes shortened and shortened. And this is because of the fact that your alpha value actually is going down drastically from a high value to a lower value. Similarly, let us look at its influence on the transconductance of the device. Now, if I plot transconductance with gate voltage for various devices, then it can be seen that as the temperature changes. So this is for the various materials. This is for the first one is 250 Kelvin, the second one is 275, and the third one is 300 Kelvin. If you look at the transconductance value, it actually falls down with higher gate and gate voltage. The general average value of the transconductance is lowered as you move from left to right hand side here. It goes down, right. Now, increasing the temperature, as I discussed with you, decreases the maximum transconductance, and this is the deterioration of alpha parameter, which reduces the on current, and therefore del ID del Vg will actually change in that case. Let us look at the impact of threshold voltage. As the temperature increases, the threshold voltage comes down drastically, and as you can see, it comes from right from 0.17 to approximately 0.11, about 0.06 volt difference, so 60 millivolt difference is there, right. To an extent, threshold voltage deterioration is mitigated by internal voltage amplification when you operate in that region of stability. Now, if you look at the capacitance modulation of capacitance matching, then again with temperature variations, then you will see that if you take the gate capacitance on the y axis and the gate voltage on the x axis, then again the capacitance actually falls down with actually higher and higher value, and this is because higher PR exhibits a capacitance matching reduction. Now, so there is a interesting physical insight into NDR to PDR, negative differential resistance to a positive differential resistance region. And people have found out that, and there's a research going on also in this case, that CFE, if you look, is actually dP dVf, and it is always less than 0, and then when it is less than 0, you go from negative differential resistance to a positive differential resistance in that case, right, and that gives you a free energy curve for ferroelectric layer. If you compare IDVG comparisons, then current versus voltage, if you find out, then there is a boost of approximately 22.5% when you use a NC FinFET, right, as compared to a traditional N channel FinFET. So the figure on the left hand side tells you that in this case, right. Similarly, if you go to the second figure, you will see that your NC FinFET has got a lower current as compared to your current here on the current. But the good part is that you have a much better subthreshold slope for a NC FinFET device. Now, this is a study which was done by many authors, and this is basically introducing trap for an NC1. So what do? You can take an FDSOI N type or an NC P type FDSOI and then insert trap and check what happens. And we see that as you go on increasing electric field, there is an increase in the value of the interface trap charge density, and that makes NC go from bad to worse in that sense. If you look at the EOL, end of lifetime evaluation, which we assume it to be 50 millivolts approximately, then typically if you have an NC FET with larger TFE is the thickness of the ferroelectric layer, then it takes more larger number of traps to have a EOL or end of lifetime, right, as compared to one which is baseline or having a smaller TFE value, right. So, which means that if you want that the device should be more reliable and carry on for a larger duration of time, advisable to keep your TFE a slightly higher value, but you need not keep it very high, because then there will be a large voltage degradation taking place across this limit. Okay. So, with this we found out an analytical expression where delta VTH is governed by the value of CFE and COX, and it is given by this expression here. And though this is not quite critical for a UG student, a PG or a research student will find this expression quite useful while realizing the trap dependency on the value of the threshold voltage. So, with this we come to the end of this lecture series, lecture 1 on negative capacitance. We have learned what is an LK formulation. We have also learned how traps influence the negative capacitance, what are the various coefficients, Landau's coefficient, alpha, beta, gamma, and how they are related and how their values change with respect to that of the threshold voltage. With this, I will like to stop here. Thank you very much.